Earthquakes.
Ah,
Powerful, unpredictable. They can literally reshape the world in seconds. But you know what? Beneath all that chaos, there's this whole fascinating world of math. And that math helps us understand, even maybe outsmart, those seismic giants. We're going deep today, like deep. This is a deep dive into that world. We're going to explore how math helps us understand, maybe even outsmart these seismic giants.
right.
We're going beyond, the dramatic news footage. We're going to uncover those equations, the models that reveal the hidden order in the Earth's tremors.
Most people, they just see these earthquakes as random, like total chaos. But actually, math gives us this lens. And through that lens, we can see patterns, probabilities. We can even see the potential for, how to prepare. We can't predict exactly when or where an earthquake will hit.
Right.
But with math, we can at least assess the risk. We can design safer buildings. We can even sometimes, give ourselves a few seconds of warning, precious seconds, before the ground starts shaking.
That's what's so amazing to me. It's incredible
Mm.
to be able to apply these mathematical principles to something as unpredictable as an earthquake.
Yeah.
So, okay, let's start with the basics here. How do we even begin to understand what's happening under the Earth's surface, all those forces?
Well, we have to think of the Earth as this dynamic system, constantly in motion, always under stress.
All right.
Imagine it kind of like a giant spring, like a really complex spring. All these different layers of rock are pushing, pulling against each other.
Okay, I'm trying to picture that, but instead of a simple spring, what if it's more like a stack of mattresses?
Yeah,
Like each layer has a different give,
correct.
responds differently to pressure.
Exactly. Some layers are stiffer, some more flexible. And that really influences how stress builds up and then how it's released. So that brings us to these core concepts. Stress and strain.
Okay.
Stress is like the pressure that's pushing down on those rocks. And strain is how much those rocks actually deform under that pressure. So it's the interplay between those two forces that leads to earthquakes.
So it's this constant push and pull,
Yeah.
this buildup of stress and strain. It's almost like the Earth is holding its breath, and then suddenly
Exhale.
Yeah.
It's a great way to put it. And that exhale, that's the earthquake.
Right.
A sudden release of energy
Yeah.
along a fault line. That's where rocks finally slip past each other. But here's the thing. That slip isn't random.
Okay.
It's governed by friction, the force that resists motion between those two surfaces.
So friction is actually holding the rocks together, preventing them from slipping all the time.
Exactly. But it's also what allows them to slip, suddenly when the stress gets too great. It's a delicate balance.
Wow.
Imagine like pulling apart two pieces of Velcro.
Okay. Yeah.
You need a certain force, right, to overcome that friction. But then suddenly it releases.
Right.
That's kind of like what happens during an earthquake.
Wow. Okay. So we've got this buildup of stress, then a sudden slip along a fault line when the friction is overcome.
Oh.
But then how does that energy actually travel through the Earth? How does it create those waves that cause shaking hundreds of thousands of miles away?
So that's where the wave equation comes in. It's this fundamental equation in physics. Describes how vibrations travel through a medium.
Okay.
And it applies to everything, like the sound of a guitar string when you pluck it,
Wow.
to seismic waves racing through the earth after an earthquake.
Wait, so the same equation that explains how sound travels also explains how earthquake energy travels.
Exactly.
That's wild.
And just like sound waves, seismic waves, they come in at different types. So there are P waves, which are compressional waves,
Okay.
kind of like if you're pushing and pulling on a slinky.
Okay, yeah.
And then there are S waves, they're shear waves, more like shaking a rope side to side.
Got it. So these different waves are basically carrying the earthquake's energy outward, rippling through the Earth. It's like ripples in a pond.
Mm-hmm.
But I'm guessing they don't all travel at the same speed, right?
You're right. The speed of those waves depends on what they're moving through, the properties of the rock.
Okay.
Imagine flicking a tight rubber band.
Yeah.
Versus a loose one. That flick's going to travel much faster on the tight one.
Right, because it's stiffer.
Exactly. Stiffer. Same concept with seismic waves. They travel faster through denser, more rigid rock.
That makes sense. But how do scientists actually use these waves to understand earthquakes? What info can they get from them?
One of the most important things is to pinpoint the earthquake's location.
Right.
By analyzing the arrival times of those P waves and S waves at all these different monitoring stations around the world, scientists can triangulate the earthquake's epicenter.
So it's like figuring out how far away lightning is by timing the thunder, right?
Mhm.
The further you are, the longer it takes for the sound to reach you.
Exactly like that. By measuring that time difference between the arrival of the P waves and S waves, seismologists can calculate the distance to the earthquake's source.
Okay. So we're seeing how math is giving us a way to locate, to even like see these earthquakes
Mhm.
happening deep beneath the surface. But what about the faults themselves, those cracks where the rocks slip? What makes them so prone to causing these massive releases of energy?
Well, that's where things get even more fascinating
Okay.
because it's not just about the fault, it's about the forces along that fault. And a big part of that complexity comes from friction. Friction on a fault isn't constant.
Wait, so the friction that's holding those rocks in place can actually change. What does that depend on?
A lot of things. How fast the fault is slipping, the history of past slips,
Hmm.
even things like the temperature and the chemical conditions in that fault zone. It's a dynamic system, and that's where things get really challenging, but also really interesting from a math perspective.
So it's this crazy, intricate dance between stress, strain, friction,
Yeah.
and the properties of the fault itself. No wonder earthquakes are so hard to predict.
Right.
Knowing that friction can change, that it's not I mean, that must make it even harder to model these systems, right?
You're absolutely right. That's why scientists are working to develop models that are more sophisticated to capture all of this complexity. There's one, it's called the rate and state friction law.
Okay, what is that? Rate and state friction law. And how does it help us understand how these faults behave?
Well, the basic idea, without getting too technical, is that the friction on a fault depends not just on the current conditions, but also on the history of past slips.
Interesting.
So how fast the fault is slipping, how much time has passed since the last slip, all of these factors influence how much friction there is at any given moment.
So it's not just a snapshot in time. We have to consider the fault's entire history to understand how it might behave in the future. That's fascinating, but also incredibly complex.
It is complex, but that's what makes this field so exciting because, the more we learn about how faults work, the closer we get to being able to assess that risk, to design safer buildings, to potentially even develop better early warning systems.
It's like we're slowly piecing together this massive puzzle, using math as our guide. But with all these factors at play, how can we even begin to predict something as unpredictable as an earthquake? Is it even possible?
That's the big question, right? And it's one that seismologists are grappling with every day. While we can't predict them with absolute certainty, math does give us tools to understand probabilities, to assess risk. And one of the key tools is something called the Gutenberg-Richter law.
Okay, I've heard that name before, but I'm not exactly sure what it is. Can you break it down for us?
Sure. The Gutenberg-Richter law is it's a mathematical relationship. It describes how often earthquakes of different magnitudes happen, and basically it tells us that small earthquakes are way more common than large ones.
Yeah, that makes sense intuitively. But I never thought of it as a mathematical law. So how does that help us understand earthquake risk?
Well, it gives us a framework for estimating the likelihood of earthquakes of different magnitudes happening in a certain area. For example, we know that for every magnitude 8 earthquake, there are about 10 magnitude 7 earthquakes, 100 magnitude 6 earthquakes, and so on.
So it's not just about saying an earthquake might happen here. It's more like an earthquake of this magnitude has this probability of happening in this area. That's much more useful.
Right, and that's exactly how engineers use that information.
Yeah.
They design buildings and infrastructure to withstand a certain level of shaking based on, the probability of earthquakes of different magnitudes happening in that specific area.
It's amazing how this like seemingly simple mathematical relationship can have such huge real-world effects. But if we can't predict individual earthquakes, can math at least help us prepare in other ways? What about those early warning systems? Do they rely on math as well?
Absolutely. Early warning systems are a great example of how math and technology are working together to help us with the risks of earthquakes. They use these networks of seismometers that are constantly monitoring for any signs of an earthquake, and then they use complex algorithms to analyze that data in real time.
So they're basically listening for those first whispers of an earthquake, those
Mhm.
initial tremors that might signal something bigger is coming.
Exactly.
Okay.
And remember how we talked about those P waves traveling faster than S waves?
Yeah.
Early warning systems, they're designed to detect those P waves first. They come first. By analyzing them, the system can quickly figure out, estimate the location and magnitude of the earthquake, and then send out alerts to the surrounding areas before the more destructive S waves and surface waves arrive.
It's like a race against time, using the speed of light and the power of math to give people those few seconds, maybe even minutes of warning.
Exactly. And those seconds can be so crucial. They can trigger automated actions like stopping trains, shutting down gas lines, even sending alerts to people's phones, just giving them time to take cover.
It's amazing. It's a real testament to how far we've come in using math to protect ourselves from earthquakes. This is all so fascinating. We've covered so much already.
Yeah.
From the basic physics of earthquakes to how those principles are being used to create, these life-saving technologies. But I'm curious, we've talked a lot about the Earth's crust and the faults, but how do we even know what's going on, deeper down inside the Earth?
Yeah.
We can't exactly dig that far, right?
Yeah, that's where things get even more ingenious.
Okay.
Scientists use something called seismic tomography. It's essentially like taking a CT scan of the Earth using seismic waves.
Oh, we're using earthquakes to see inside the Earth.
Exactly. It's brilliant.
Okay.
By analyzing how those seismic waves travel through the Earth, their speed, their path, how they refract and reflect, scientists can create this 3D map of the Earth's interior.
That's incredible.
Yeah.
So we're not just using math to understand the earthquakes themselves. We're using it to unlock the secrets of the Earth's interior. It's like this giant puzzle, and each earthquake is giving us a new piece to fit in.
That's a great way to put it. And the more pieces we have, the clearer the picture becomes.
Right.
And that's what makes this field so captivating. We're constantly learning, constantly refining our understanding of our planet and the forces that shape it.
This is remarkable. We've only just scratched the surface, but I feel like I've already learned so much.
Yeah.
But before we go any further, let's take a moment to think about what we've covered. We've talked about stress, strain, friction, those fundamental forces that drive earthquakes. We've explored how that wave equation helps us understand how earthquake energy travels and how scientists use those waves to locate earthquakes, even to map the Earth's interior.
Right.
And we've even touched on how math is being used to develop those early warning systems that can potentially save lives.
It's been quite a journey so far. And what's even more exciting is there's so much more to explore. In the next part of our deep dive, we're going to delve deeper into the challenges of earthquake prediction, the efforts to develop even more, sophisticated models, and the potential for new technologies to help us better understand and mitigate the risks of earthquakes.
I can't wait.
It's mind-boggling when you think about all the factors that are at play with earthquakes. Every single tremor, it's like a fingerprint. It's unique in how it started and the path of destruction it takes.
It really is. And that makes me wonder about, the holy grail of earthquake science prediction. Is it even possible to accurately predict when and where that next big one will hit? Or are we forever chasing a moving target?
The million-dollar question. If we could reliably predict earthquakes, it would be a total game changer. Think of the lives we could save, the damage we could prevent.
Right.
The Earth it's a complex system, lots of surprises.
So even with all our advances in math and modeling, are we still a long way off from accurate earthquake prediction?
I wouldn't say we're a long way off, but there are definitely, hurdles we have to overcome. Remember when we talked about the rate and state friction law and how friction on a fault isn't constant?
Right.
That variability makes prediction incredibly difficult.
Because even if we know where a fault is and we understand the stresses that are building up, we can't be sure exactly when that friction will hit its tipping point and trigger the earthquake.
Exactly. It's almost like trying to predict when a pile of sand will collapse.
Okay.
You can keep adding those grains of sand one by one, but you never know for sure which grain will cause that avalanche.
So it's not just a lack of data or computing power that's holding us back. It's the Earth itself. It's so complex and unpredictable.
You got it. But, that doesn't mean we're giving up. Scientists are always working, refining those models, incorporating new data, trying to develop these, really innovative approaches to earthquake prediction.
That's good to hear. But in the meantime, if we can't pinpoint the exact time and location of every earthquake, what tools do we have to help us prepare and mitigate the risks?
Well, one of the most valuable tools is the concept of seismic hazard.
Okay.
By combining, historical data on past earthquakes with our understanding of fault lines, with the geological conditions, and of course mathematical models, we can estimate how likely it is that different levels of ground shaking will occur in a given area.
So it's kind of like a probability map
Yeah.
showing us which areas are more likely to experience, stronger shaking based on
Yep.
past patterns and geological stuff.
That's a great way to put it. And that information is crucial for things like building codes and land use planning. It helps us make smart decisions about where we build, how we build, and what kind of safety measures to put in place.
So while we can't say an earthquake will happen here on this date,
Mm.
we can at least say this area has a higher chance of experiencing strong shaking, so we need to make sure, the buildings are built to withstand that.
Right. It's about managing the risk, not trying to eliminate it entirely, and
Right.
that's where math is so powerful. It lets us actually quantify that risk, make informed decisions, and in the end, build more resilient communities.
Yeah. It's amazing how math can literally save lives.
Mm.
But I'm curious, how do these models account for all the variability in the Earth's structure?
Hmm.
We've talked about how different rock types and layers affect, how waves move, but it seems like there would be so many variations to consider.
You're right. It's one of the biggest challenges in earthquake modeling,
Yeah.
capturing all that complexity. It's not just about knowing where the faults are, it's about understanding the properties of the rocks around those faults, how they behave when they're under stress, how fluids interact with those rocks.
It's like trying to model a giant 3D jigsaw puzzle where all the pieces are constantly moving and changing.
And yet scientists are making incredible progress.
Yeah.
They're always incorporating more and more detailed data
Yeah.
using these sophisticated mathematical techniques and leveraging, the ever-increasing power of computers
Right.
to create models that are more accurate and more comprehensive.
So it's a work in progress, a constant refinement of our understanding as
Yeah.
we get more data and develop better tools.
Absolutely. And as computing power continues to get better and better, and as we learn more about how the Earth works, those models will only get more powerful and more insightful.
That's encouraging. But with all this talk about models and probabilities, it's easy to forget that we're dealing with, real world events that can be devastating.
You're right. And it's important to acknowledge that human side of it all.
Yeah.
Behind all the math and science, there are people whose lives are really affected by these events.
Which brings me to another question. We've been focusing a lot on the technical stuff, but what about that human element? How are communities using this scientific knowledge to prepare for earthquakes
Right.
and to respond effectively when they do happen?
That's a really important aspect. And there's a lot of great work being done in this area. For example, there are communities all over the world that are starting to implement these earthquake early warning systems,
Yeah.
not just for, big infrastructure, but also for individual homes and businesses.
So people could potentially get alerts on their phones or other devices,
Yep.
giving them those precious seconds to take cover before the shaking starts.
Exactly.
Oh,
And these systems, they're being integrated with smart home technology, so they can automatically trigger certain actions like shutting off gas lines or opening garage doors to give people, escape routes. It's about giving individuals the power to take those steps to protect themselves and their families.
that's incredible. It sounds like we're moving toward this future where technology and math are working together to create this safety net for people who live in earthquake-prone areas.
And it's not just about technology either.
Right.
There's also a growing focus on these community-based preparedness programs,
Yeah.
educating people about earthquake risks, teaching them how to, secure their homes, practicing earthquake drills. It's about building a culture of preparedness so that when an earthquake does hit, the community is ready to respond effectively.
It's really inspiring to see how scientific knowledge is being turned into real-world action. It's empowering communities to be more resilient when faced with these incredibly powerful forces.
And that's what it's all about, really. We're not just studying earthquakes for the sake of knowledge. We're studying them to protect lives and build a safer future for everyone.
Well said. This deep dive has been like a whirlwind of information. But I feel like we're finally starting to see the bigger picture. We've explored those fundamental forces behind earthquakes, the challenges of prediction, the innovative ways we're using math and technology to reduce the risks. But before we wrap up, I want to touch on one final and maybe the most interesting aspect of this whole thing: the future of earthquake research.
Hmm.
What what are those big unanswered questions that scientists are still trying to figure out? What are those breakthroughs that are on the horizon? What are you most excited about when it comes to the future of this field?
Those are the questions that keep me up at night. And the amazing thing about science is that there's always something new to discover.
Right.
Always more to learn. One area that I'm particularly excited about is how artificial intelligence and earthquake science are starting to intersect. We're at this point now where we can feed massive amounts of data into these machine learning algorithms, and we can train them to recognize patterns and make predictions that we as humans might miss.
So we're basically teaching computers to be earthquake experts.
In a way, yes.
Wow.
These algorithms can sift through like mountains of seismic data. They can identify these subtle signals and correlations that could be pointing to future events. It's still early, but the potential is huge.
It's like having this digital detective, constantly searching for clues that might help us anticipate earthquakes.
Mm.
But AI it's not a magic solution, is it? What are some of the challenges with using these technologies for earthquake prediction?
Well, one challenge is just the sheer volume of data.
Right.
We've got, decades of seismic recordings, geological surveys, all kinds of information, but it's not always organized
Okay.
or easy to access. So we have to figure out better ways to manage and analyze these massive data sets.
No, it's not just about having the data. It's about being able to make sense of it all, to find the signal within all that noise.
Exactly. And that's where AI can be really helpful, but we also have to be careful about, relying too much on AI. These algorithms they're only as good as the data we train them with,
Right.
and sometimes they can make mistakes,
Right.
or they can misinterpret patterns.
So it's all about finding that balance
Yeah.
between, using the power of AI, but also being critical,
Yeah.
recognizing that it's a tool.
Mhm.
It's not a replacement for human expertise.
Exactly. We have to use AI responsibly,
Right.
always, questioning its output, making sure its findings line up with what we already know about earthquake science.
It's like having this really brilliant assistant, but one that still needs, some guidance and supervision.
Hmm.
But beyond AI, what other exciting developments are coming up in earthquake research?
One area that I'm really interested in is the study of induced seismicity.
Okay.
This refers to earthquakes that are actually triggered by human activities, things like oil and gas extraction,
Yeah.
or geothermal energy production.
So we're not just talking about natural earthquakes anymore, but earthquakes that we might be causing without even realizing it.
That's right.
Wow.
And as we shift to more sustainable energy sources, understanding and managing induced seismicity is becoming even more important.
It's like a whole new dimension to
Yeah.
the earthquake puzzle, and one that we've barely started to explore.
And it's a complex puzzle because induced earthquakes, they often happen in areas that haven't had natural earthquakes in the past.
Right.
So we don't have, that same historical data to work with.
So we're having to develop new models, new ways of thinking to understand these human-triggered earthquakes.
Exactly. And that's leading to some really fascinating research into, how fluids interact with rocks, how changes in pressure within the earth can cause faults to slip, and how we can minimize the risks that are associated with these activities.
It's a reminder that we're not just watching the earth, Our actions have consequences, and it's our job to understand those consequences and find ways to make sure those impacts aren't negative.
Well said. And I think that's a really important takeaway from our deep dive today. Earthquakes are powerful, but we're not helpless.
Right.
Through science, through math, through innovation, we're constantly learning more about how to understand, to predict, and to live safely with these seismic events.
This deep dive has been incredible. We've gone from like the basic physics of earthquakes to the very cutting edge of research, and I'm even more fascinated by this topic than I was before. But there's one question I just have to ask before we move on. If you had a magic wand and you could make one major breakthrough in earthquake research, what would it be?
Ooh, that's a tough one. But I think, the ultimate goal would be to find a way to reliably predict earthquakes.
Right.
Imagine being able to say with certainty when and where the next big one will hit.
Wow.
That would change everything about how we prepare for earthquakes, and it could
Yeah.
potentially save, countless lives.
Yeah, it would be a game changer for sure. But for now, we have to rely on those amazing tools that math and science have already given us.
Right.
Assessing risk, designing safer buildings, developing those early warning systems. But who knows, maybe one day that magic wand will become reality.
I have no doubt that, with more research and innovation, we'll keep making progress toward that goal.
It's kind of humbling,
Yeah.
to think that with all our advances, earthquakes still have this element of mystery. We can analyze all this data, build those complex models, but the Earth, it always has the potential to surprise us.
That's part of what makes this field so compelling. It's a constant process of discovery,
Hmm.
refining what we know, pushing the boundaries of our understanding.
So where do we go from here? What are the frontiers of earthquake research that you're most excited about?
One area that I think has huge potential is where artificial intelligence and earthquake science are coming together.
Okay.
We can now feed these vast amounts of data into machine learning algorithms, and we can train those algorithms to see patterns, to make predictions that we as humans might completely miss.
So we're essentially teaching computers to become like earthquake experts.
Kind of, yeah.
That's wild.
These algorithms can sift through so much seismic data, mountains of it, and they can pick out those really subtle signals, those correlations that might point to future events. It's early days, but the potential is really exciting.
It's like having this digital detective constantly working, looking for those clues that could help us, anticipate earthquakes.
Yeah.
But AI it's not a magic solution, right?
Yeah.
What are some of the challenges when it comes to applying these technologies to earthquake prediction?
One of the biggest challenges is just the sheer amount of data.
Right.
We have decades of seismic recordings, geological surveys, tons of information,
Right.
but it's not always organized in a way that makes it easily accessible.
Right.
So we need to get better at managing and analyzing these massive data sets.
It's not just about having the data, it's about making sense of it all, finding the signal in all that noise.
Exactly. And that's a place where AI can be really helpful. But we also have to be careful about, becoming too reliant on AI.
Yeah.
Because these algorithms, they're only as good as the data that we use to train them.
Right.
And they can, sometimes they make mistakes. They misinterpret patterns.
So it's all about finding that balance, right?
Yeah.
Between using the power of AI, but also, maintaining that critical eye.
Yeah.
Recognizing that it's a tool.
Right.
It's not a replacement for human expertise.
We have to use it responsibly. Always questioning what it's telling us, validating those findings against what we already know about earthquake science.
It's like having this brilliant assistant,
Yeah.
but one that still needs, some guidance, some supervision.
Yeah.
But beyond AI, what other interesting things are on the horizon for earthquake research?
One area I'm personally really interested in is the study of induced seismicity. And this is basically earthquakes that are triggered by things that we do, like oil and gas extraction, geothermal energy production.
So now we're not just talking about natural earthquakes, but earthquakes that we might be accidentally causing.
Exactly.
Uh,
And as we move towards these more sustainable energy sources, understanding and managing induced seismicity is becoming more and more important.
it's like this whole new layer to the earthquake puzzle that we're just starting to uncover.
Yeah, and it's a complicated one because these induced earthquakes, they often happen in places that haven't had a history of natural earthquakes. So
Right.
so we don't have the historical data to work with.
So we're having to come up with completely new models,
Mm-hmm.
new ways of thinking to understand these earthquakes that humans are triggering.
Yeah, exactly. And that's leading to some really interesting research on, how fluids and rocks interact, how changes in pressure within the earth can cause those faults to slip, and how we can reduce the risks that come with these activities.
It's a reminder that we're not just passively observing the Earth.
Mm-hmm.
Our actions, they have an impact.
Hmm.
And it's up to us to understand those impacts
Right.
and to try to minimize any negative effects.
Well said. And I think that's a really key takeaway from our deep dive today. Earthquakes are a force of nature. They're powerful, but we're not powerless against them.
Right.
Through science, through math, through innovation, we're learning more and more about how to understand them, to predict them, and ultimately to live more safely with these seismic events.
This deep dive has been amazing. We've explored, the basic forces at work, the challenges of prediction, the incredible things we can do with technology, and the exciting future of this whole field. And it's clear that even though earthquakes might always have some element of mystery, our journey to understand them, it's far from over.
And that's what makes it all worthwhile. Every new discovery, every step forward brings us closer to this future where we can live in greater harmony with our planet.
Thank you so much for taking us on this deep dive. It's been eye-opening, inspiring, a real exploration of the world beneath our feet. And to our listeners, we hope you've enjoyed the journey too. Until next time, stay curious, stay informed, and stay safe.